jump into the second half of chapter 7, we're going to start talking about a new type of function called a periodic function. And periodic functions are functions that I would say behave very consistently. In fact, the definition of a periodic function is a function in which a basic shape is repeated over and over indefinitely, meaning without end, to the left and the right. So what we have in front of us is a periodic function. The window of this graph paper goes from like -15 to 15, but it could keep going. But what we see repeated is this shape right here. Almost looks like a little parabola. And if I were to pick this parabola up and slide it exactly to the right or to the left, it would lie right on top of itself. And what's really important to note about a periodic function is that the pattern of the y values is what's repeating. So the y values repeat over regular or consistent intervals, right? So this graph right here goes from 0 up to 4, back to 0, and it takes it 4 units to do that. Does that same thing again, 0 up to 4, down to 0, and it takes 4 units to do that. And it just keeps repeating over and over and over again. So this is, it's not a multiple choice question, but it says, which of the following graphs are periodic? It's essentially a yes-no question for these 4 graphs. So as we take a look, we're going to ask, do we see the same set of y values getting repeated over and over and over again? So this first graph, it looks a little bit different for us, but the idea is, and I'm going to just kind of start in the middle, I see this shape right here. And this shape looks like we see the exact same thing. It's just slid over. And then we see it again. It's just the same graph that's been slid to the right. Or we could go backwards and slide that pink graph to the left. So I would say yes, this first graph is periodic. The second graph has a lot of symmetry, has a lot of similar pieces. However, if I start right here in the middle, this little piece, if I slide it over, that's not what I get. Even if you looked at it as a bigger picture, like this piece right here, if I were to slide that piece over, it would look like that. So while you see the same shape, almost it's growing, right? And the y values are changing. So we want to be very careful with how we define a periodic function. And when I say the y values repeat, that's really important because here the y values are actually getting bigger as we go. So this is, while it's symmetric, it is not periodic. Okay, it's growing over time. Let's take a look at this one in the bottom left-hand corner. We see a lot going on with this one. And when I talk about a basic shape, I mean, I kind of looked at it like a W. I see this W, and if I pick that purple W up and slide it over, I see it again. Or if I pick that purple W up and slide it to the left, I see it again. So the y values are staying the same, right? The highs are the same y value, the lows are at the same y value, and it's just this W shape getting slid around, so getting slid side to side. So yes, this is a periodic function. When I take a look at the next one, it's almost like a wave, right? And so maybe I just start at the top of the wave and I dip down and then I come all the way back up to the top. So you see there's my basic shape is the term I referred to earlier. And if I take this wave, there it is again. It kind of runs off the page, doesn't it? Or slide it to the left, there it is again. Or slide it to the left, there it is again. Okay, so this last one is periodic. So as we talk about periodic functions over the next few weeks, one of the most important characteristics or qualities of a periodic function is to talk about the period length. And the period length is essentially how long does it take to complete one cycle. When we say how long, we're kind of thinking time. And so for us, time is like the x-axis. So what is the horizontal distance between the starting and ending points of one complete cycle? So this is the same graph that we had on slide number 1. And I could even pop up and look at it, but I even use these 2 colors, right? So we said this basic shape gets repeated over and over and over again. And when I want to talk about the period length, I'm talking about how long does it take from beginning to end. Well, this period sits between 0 and 4, so the period is 4 units long. When you look at the next one, same thing. This one sits between 4 and 8. It's still 4 units long. Now, some of you might say, well, what if I looked at it a little bit differently? I'm going to use a yellow marker here. What if you looked at this basic shape as starting at the top, dipping down and coming back up to the top, almost like a bird you used to draw in like elementary school art class? Because to me, that shape is getting repeated over and over and over again. See, there's another one. From top to top. But what doesn't change is the period length, because if I come down here, this green graph or green portion sits between -10 and -6, which is still a distance, horizontal distance of 4 units. Okay. All right. So we're just going to look at a few different periodic graphs. We're going to state the domain and the range, and then of course now the period length. And I know there's not a lot of room here. I'm just going to write everything underneath here. So we're going to do the domain, we're going to do the range, and we're going to do the period length. Now, domain and range, those are old questions for us. However, what I want you to understand that in a periodic function, we already said in the definition it repeats indefinitely, which means this graph is going to continue to go on forever and ever and ever and ever. So domain, remember, are our x values. We are using all of the x values starting way back at -infinity and continuing on to positive infinity. My range, however, remember, is our y values. And when you look at that graph, this entire graph sits between the x-axis and then all of these y values of 4. There's nothing down here and there's nothing above 4. So my range starts at 0 and touches 0, so I'm going to include it with a bracket, and the highest this graph ever gets is 4. And it does touch 4, so we'll put it in a bracket. All right, let's talk about the period length. I'm going to use my orange marker here. I wanted you to look at this graph and identify, and use a highlighter, one complete cycle. And you can look at that a lot of different ways. When I first looked at this graph, I saw a big old W that got repeated over and over and over again. That's one way to look at this graph. Another way to look at this graph is tall mountain, short mountain. Tall mountain, short mountain. I used green there. It doesn't matter as long as you're looking at what's getting repeated. And if you go tall mountain, short mountain, 1, 2, 3, 3 units long. If you get your W, I'm again just looking at where does it start and where does it end, same thing, 1, 2, 3. So no matter how you look at this graph, each cycle is 3 units long. Okay, well, let's do the same thing for this second graph. Again, we're going to talk about the domain, we're going to talk about the range, and we're going to talk about the period length. Again, periodic graphs repeat over and over and over again. The domain is going to go on forever and ever and ever, -infinity to infinity. The range, this graph bottoms out down here. Well, we got to look at our scale. Look at our, it changed a little bit on us. So it looks like this would be -6. And the very top of this graph is up here at 8. So my range goes from -6 to +8. Remember, range has to go in numeric order, so we're going from smallest to biggest. And now grab that highlighter again, or whatever it is that you're using, and I want you to look at one complete cycle. I look at it as going from the top to the bottom, back up to the top, and then starting over again. You might be looking at it as bottom, top to bottom, almost like an upside down of the same shape. What doesn't change, however, is the length of the period. This graph, I'm going to use my purple one, started here at -15 and ended here at -5. So that horizontal distance is 10. Same thing with the yellow. It started at x equals 0 and it ended at x equals 10. So the length of one complete cycle is 10. So the period length of the graph is 10. All right, let's flip it over. We're going to do that same thing with two more graphs. Okay, so I just repeated the directions here. So we're going to do the domain, we're going to do the range, and we're going to do the period for both of these. Okay, so let's take a look at this top graph here. Again, this is going to keep going on forever and ever and ever, side to side. The range, the bottom y value is -2, the top y value is +1. So my range is -2 to 1. And then I'm going to go in with my yellow marker. I'm going to mark one shape. And again, you look at this however you want. I see that shape getting repeated over and over and over again. And that shape sits between -3 and +2. So the length of this graph is 5. Let's take a look at the next one. Domain, -infinity to infinity. The range, now look at the scale on the axis. So let's be careful. It looks like each block will be worth 10. So let's see, the bottom of this graph sits down here at -30. And the top of the graph is up here at 20. So my range goes from -30 up to 20. Let's talk about our period length. Now, interestingly enough about the x-axis, look, it's labeled in pies. All right, we'll come back to that. I mean, pi is just a number. We can count by pies. We've been doing that in the unit circle. So I want you to go look at one complete shape. What's one cycle that's going to get repeated over and over and over again? So let's see, I've got a horizontal segment, and then a parabola. And then it starts over. Horizontal segment, parabola, horizontal segment, parabola. So when I look at this graph, it is starting here when x equals 0, and it is ending here, unfortunately, at some unknown x value. I don't want to say unknown, right? But if 2 blocks is pi, then this would be half of pi, or pi over 2. Think about our unit circle, right? If pi was half the circle, half of it was pi over 2. We can just start counting. 1 pi over 2, 2 pi over 2, 3 pi over 2. So even though the x-axis was labeled differently, I mean, we can still count the boxes. We just have to know how big each box is. Okay. All right. So let's take a look at this next one. It says a complete period of the graph of h of x is shown below. So a complete period. So starting from -7 and going to -2. Finish the graph on the interval -12 to 12, given that it is a periodic function. Oh, well, they showed us one period. We're just going to keep it going. I've got 1, 2, 3, 4 pieces to this period. We're going to go down 2 over 2. We have a horizontal section. Then we're going to go up 2 over 1, and we're just going to have that little horizontal section at the end. So down with a slope of -1, horizontal. Up with a slope of 2, horizontal. And we're just going to repeat that until we get to 12. And then I'm going to go the other way. So let's say we finished horizontal, slope of 2, horizontal, and -1. So essentially I'm just picking this up and I'm sliding it in both directions. Okay. Well, again, this graph is just going to keep on going. It's going to use every single x out there. The range of this graph bottoms out at 2, caps out at 4, maxes out at 4, I guess. And then I have 4 questions for us. mean, these are not new questions, but it's asking us to find h of 0, h of 7, etc. Well, remember, h of x, that's the y value. H of x is the same as y. So I'm giving you the x, you're spitting out the y. We know that. This means find the y value when x equals 0. Well, go look at the graph. When x equals 0, the y value is 2. Let's look at this question. H of 7. Find the y value when x equals 7. Okay, let's go to the graph here. 6, 7. Oh, the y value is 4. All right, well, this is easy. Negative 10. H of negative 10 says go find the y value when x is negative 10. Okay, negative 10. The y value is 2. And then it says find h of 24. Oh my gosh, 24 is way off the page. And I don't necessarily want to extend my graph in order to do that. But let's keep in mind that this graph is periodic. It's going to be these same y values over and over and over again. So the first thing I'm going to do is find the period. We haven't really done that yet. This graph they gave us started here and ended here for a length of 1, 2, 3, 4, 5. Which means every 5 units I'm going to end up at the same place. So if I'm trying to find h of 24, every 5 units it's going to be in the same place, the same y value. So if I subtract 5, I get 19. Those should be the same y value. Excuse me, h of 24 and h of 19 should be the same y value. But h of 19, I still don't see it, so let's subtract 5 again, and I get h of 14, which is closer. Let's subtract 5 again, and we get h of 9. Oh, h of 9 is 3. And so if h of 9 is 3, then h of 14 is 3, which means h of 19 is 3, which means h of 24 is 3. A big deal to note is that this graph will have a y value of 3. I'm just going to look on the downslopes here. Here, 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 here. And what do you notice about these points? They are 5 units away from each other. So even if I'm not looking at the beginning to the end of the period, I'm just saying this point will be at this same place 5 units later. And so I use that to help me find a y value on a graph that I couldn't see. Okay, good. All right, let's do the same thing with this next one. Definitely change the scale on the axis. But same idea. Here's a portion of the graph of f. It's a complete period of a periodic graph. I want us to finish the graph from negative 360 to 360. That sounds familiar, thinking about like the unit circle. And then we'll answer any of the questions that we have. So this graph goes from the top to the bottom, back to the top. In fact, I would even say halfway through it's at 1. There's like 5 points I can use. So it's at 4, then 1, then negative 2, then 1, then 4. So let's repeat that. 4, then 1, then negative 2, then, well, they asked us to stop. Okay. So it's kind of like a wave, so we'll kind of finish that wave. And we'll go backwards. So we're at 4. We're going to go 1, negative 2, 1, 4. And there's that wave shape again. And keep going. 4, 1, negative 2, 1, 4. And we'll keep going. And that gets me back to negative 360. So look at that same wave shape. We've seen that a couple of times now today. Right? So it wasn't linear. Don't make it jagged. Right? It started to curve at the top and the bottom, didn't it? Okay. All right, well, let's see. What is f of 0? Well, again, that means find the y value when x equals 0. Oh, it's negative 2. I'm going to skip to this one just because I don't see that number on the graph, but it's not that hard. F of negative 270. Oh, same thing. Here's negative 270. The y value is 4. Let's think about this for a second. 135. Pause. On this graph paper, I've labeled every other box. just like I've been doing all along with the y-axis. If 2 boxes is 90, that means 1 box is 45. So there's 1 times 45, there's 2 times 45. This would be 3 times 45, which is, 135. It's halfway between 90 and 180. So what is the y value there? It's 1. Okay, let's answer these last few questions. It says, use your graph on the previous slide to solve each equation over that interval negative 360 to 360. So they're saying only look in this window, but let's solve these 3 equations. So remember, f of x means y. They're saying find x when y equals 4. Well, I think that's going to happen a lot, right? Here's 4. The y value is 4 here, and here, and here, and here. So that's going to happen at negative 270, negative 90. So let's go write that down. So x equals negative 270, x equals negative 90, x equals 90, and x equals 270. So in this interval, there are 4 different x values whose y-coordinate is 4. Okay. Let's look at the second question. It says f of x equals negative 3. So they're saying find the x when y equals negative 3. Find x when y equals negative 3. All right, here's negative 3 down here. Oh, the graph never gets down there, does it? So I'd say no solution. The graph doesn't get lower than negative 2, does it? And then the last question says, a little bit different because it doesn't say f of x equals, it says f of x plus 2 equals 0. Well, gosh, that's an easy fix. Let's move that negative 2 to the other side. Now, okay, it looks just like the last few we've done. So again, it's saying find the x when y equals negative 2. And I think that does happen. It happens a lot, doesn't it? Here's negative 2. That happens here, and here, and here, and here, and here. So I have 5 answers I'm going to go write down. Negative 360, negative 180, x equals 0, x equals 180. So maybe I can turn that negative into a plus or minus, positive or negative 180, and then same thing with the 360. I could have done that up here. I didn't, but 1, 2, 3, 4, 5 solutions.